Hello and welcome. In this video, I will be talking about some introductory part to system Verilog version of UVM RAL, register abstraction layer. Already we covered some topics in last few videos related to this RAL. And the covered topics I have highlighted here. Okay, so we discussed the basic introduction to UVM RAL, what RAL is all about. Then we discuss what is a front door method and back door method, which is faster and why. We discussed that. Then we already had a discussion about the types of prediction. Auto prediction, which is also referred as implicit prediction. Then passive prediction and the explicit prediction. Okay. Then we discussed how we can define the memory class as well as the register class with respect to RAL as a part of a RAL. Okay. Then we also discussed the register database. In that video, we discussed that if our DUT has some registers and memory in it, how the database will be there, register database will be there. So each register will have a pair of a desired and mirrored value, and for memory there is no any desired and mirrored value. Okay. So what is desired value? What we think in the hardware register, what we want in the hardware register next. This is what desired value. Or you can consider the value of the register for a next transaction. What is mirror value? It is like what we think in the hardware register now. Okay. And we discussed this desired and mirrored value will updated by the predictor at each front door write and read axis. Then we discussed some base classes related to RAL. If we are defining register, then how we can access that register, how we can define that register by extending it from UVM range class. Then for that we have to define some fields. Then how we can define fields using UVM range field. Then we discussed this UVM range file, which is the optional one. If you want, we can add or we can remove it. Then we discussed the memory base class. If our DUT has memory in it, how we can define the memory as a part of RAM. Then the register map, and the last one is UVM reg block. So what is UVM reg block? It is nothing but a register block, and it will consist of a map. So this map will have the offset address of all registers and memories. In addition to offset address and of register and memory, will have the pointer for adapter and sequencer in. Okay. Now here in this video, I will just walk you through a concept that if our DUT has a single register in it, how we can verify that using this register abstraction by considering a front door access. And in the later part, we'll try to understand the backdoor access too. So some basics for RAL, minimum requirements for including RAL in our test bench architecture. There are some minimum requirements that should be there. Then only we can add this register abstraction layer in our test bench architecture. What are those? So first requirement is at least our DUT has a single register or memory in it. if our DUT has a register as it is defined over here, then it should have at least a single field in it. And the register should have an address map. So these are the three minimum requirements for including RAL, register abstraction layer, in our test bench architecture. Remember this, it is important. Now let me just give you the overview, the test bench architecture overview if we are adding the RAL in our test bench architecture. So this is what our DUT we are considering. It has single register in it. And we are considering the front door. For that we should have the agent. It should have sequencer and driver, so this driver can drive the stimulus to the DUT through this interface. And we have to define the register model. Okay, so this register model will have the desired value and mirror value variables. Along with it should have register map. So this register map will have the base address and the instance of a register. Let me just walk you through the code, how we can define a register model for the DUT which has a single register in it. So let's consider our DUT has a single register in it. So I have defined a DUT code over here, as you can see on the screen, that this DUT has a single register in it. So this module DUT and module DUT, in this I have defined some input and output variables for that DUT. Those are logic type, clock, reset, address, and the write enable. So this write enable is one, then we are writing the data inside a DUT. If it is 0, we are reading the data inside with the help of this output ODM. Now as a part of this DUT, as I told you that we are defining simple one register. So logic 7 down to 0, temp reg 0. This is the internal register of a DUT. Now the code is here. The real logic for that is always block I'm using, always underscore ff at the rate posh of the globe. I'm using system Verilog version of HDL to define hard. If reset is there, then the register content will be 0. Else, if the write enable is there and the address is 0, then the input should be there. Input will apply, adding inside this register, restoring inside this register. Else, if the write enable is 0, we are just reading the content of this register on this dout port if address is 0. Very simple. And just we are here defining the interface as a part of this DUT. Interface and in interface. In that I am defining all the input and output ports as a logic. So this is what a simple DUT. Okay. Just we are commenting it out because we are not applying any stimulus to the DUT. Just we'll take a simple example that our DUT has one register in it. How to define a register model for that. Okay, so as a part of this video, I'm not explaining you the adapter layer over here and the agent and all. Just we'll define a register class, then we'll define one register block. In that, how we can add this register and how to create and configure. I just walk you through as a part of this video. In the later video, we will try to see the complete example with the code. So tick include UVM macros.svh and import UVM package : star. These two lines are mandatory in order to get an access of UVM macros and all UVM classes. Then remember, I told you that if we are defining our own register class, then we have to extend it from UVM reg over. So class register 0, which is extending from UVM reg. And remember, as a part of register all the classes are the object classes. So we have to register them using object utils factory registration method. So for this RAL, for this register class, take UVM object utils, and we are defining a single field for this register, and we are defining it as a rand, so that in future if we can randomize, make use of random, we can randomize this property for this field. We can randomize. So UVM reg field F0 is a field for this register. Single field we are considering because it is a minimum requirement for us that at least single field should be there for the register. Then as it is an object class, its default constructor expecting one argument. Along with this one argument name, we are providing two additional arguments over here. So this 8 is a width for this, register field. Width of a register we are defining as a part of this constructor, and we don't want any separate coverage for this register. Hence, the third argument should be UVM no coverage. Then, as it is an object class, we cannot define phases over here. So the executable logic we need to define inside a virtual function void build, where we are defining one function build, and inside that we are creating this field F0 which we have defined over here using factories create method. So how to create F0 is equal to UVM reg field type ID create. Okay, and as a part of this function build, we have to define one configure method, and this configure method will have some 9 arguments in it. So parent, size, LSB position, type of access, volatile in nature, reset value, has reset, is rand, and individual accessibility. So these are the 9 arguments. So if you want to remember how we can remember this, I have remember this like this PSL AVR high. You can make your own technique to remember. How I am remembering, I just walk you through that. So this PSL I am considering parcel. You can take any one of it. AVR means arrive, and HII high. And how I am making this, how I am remembering this is like this simple technique. And now we will map this PSL AVR high, parcel arrive high. Okay, so this PSL means this dot parent dot size dot LSB position, these 3 arguments. Then AVR, just I am considering arrive. So dot access dot volatile dot reset AVR. Then HII high means has reset, is rand, and dot individual accessible. You can make your own technique. Let me just walk you through all these arguments, 9 arguments. Dot parent is a current class, hence in the parenthesis we have to give this. So this will refer to this register R0 class. Then the size is nothing but the width we have to define, which is 8 in our case. Okay, you can see over here also. Then the LSB position for this is 0. Okay, so if you see over here, this is what the right hand side is LSB for, and this this left hand side is a MSB, okay, for this register. So this is what the LSB position 0 we are considering. The type of access, it should have this read write access, read only, write only access. So generally we are defining read and write access. So we'll understand this access policy in the later videos. We'll understand that, but as of now just consider this field has both the access read and write. Then dot volatile, if it is 1 means the field can't change between consecutive accesses. Dot reset is the reset value, power on reset for this field is 0. Then hash reset means the field support the reset or not. So hence we are giving in the parenthesis one. Is rand, meaning the field is capable of accepting the randomized things. So field can be randomized, hence when the parenthesis we are giving 1, meaning this field support the random. Okay, randomized method. Then dot individual accessible, meaning this field whether it is individually accessible or not. So in the parenthesis we have to provide 1 if we want this field to be individual accessible or not. So this is what the 9 arguments you can remember with this simple technique. Parcel arrived high, PSL AVR high. You can make your own technique too. Okay, so remember, as a part of simple test bench architecture only we have to define these things. But let's consider our DUT is a bit complex. It has 1000 number of registers. Then defining our own methods, this register and all, it's a bit complex. So for that there is automation is there. We'll see that concept later. So we are not defining the IP exec file is there, that if we are just providing the information, register information, it will automatically, tool will automatically generate the register model for us. But for our understanding, we are just considering a simple example how to define all the things. Now the register block, which is the top one, which is extending from UVM bridge block. It is also an object class. We have to register the tick UVM object details factory registration. Then here we have to define the instance of this register. Register 0, register 0, H is the instance for this register R0. Okay, sorry, register 0. R0, register 0, H is the instance for this register 0. Okay. Then as a part of this class, we have to define the default constructor. As it is an object class, its default constructor expecting 1 argument. Along with, we have to define the second argument is UVM no coverage, because we don't want any separate coverage for this register block. Now as a part of this register block, we have to define one build method. Okay, so virtual function build. Okay, here we have to define, as it is a void, it is not returning anything, we have to define it as a void. Then here we have to create the instance for this register. We have to allocate a memory for this register instance using factories create method. So register instance, register name, type ID and create, and we have to call the build method of this register. So as you can see, build, it will, this register instance dot build will call this build method of this register, which has configure information for this field. Then we have to define the configure method for the instance of this register 0h dot configure, and this will refer to the current class. So current class is register block here. Then here we have to define a create map. Okay, so default map is equal to create map, and in the parenthesis we have to provide 4 arguments. So first is the instance default map, then the second one is a base address, third one is the size in byte. So the field, as you can see over here, is of 8-bit, right? So 1 into 8 is equal to 8, right? So that's why we have to define the size 1, which is in byte, and the fourth argument will be UVM little endian. So what this little endian, let me show you. If you see the literature, you will find that this create map, we have to provide some arguments. So 4 are mandatory: the name, the base address, the size in byte, and the endian. So what is this endian means? Let me just show you. So this endian means UVM Indianness underscore E type 1. Okay, so it specifies the byte ordering. Okay. So if you are defining UVM no Indian means byte ordering not applicable. If you are defining UVM little Indian, then least significant byte first in the consecutive address. Then you can define UVM big Indian, UVM little 50, big 50. So mostly we are defining only UVM little Indian. So least significant byte in first in the consecutive address. So the fourth argument will be UVM little Indian. Then we have to add this register inside this map up. So what is for that, there is a method called add reg, and inside this we have to provide 3 arguments. Okay, so you can see on the screen in the parenthesis we have to define 3 arguments. So first, default map dot add reg, inside this parenthesis this 3 arguments, the instance of the register, then the offset address. So here offset address we are considering 0, and the type of access. So generally we are defining here read and write access. So if you see the literature, you will find this add reg method. Okay. Add reg, and here you'll find it should have some arguments. So mandatory one, first 3 only: instance, the offset, and the type of access. Then we have to define one lock model. It is mandatory. So what this lock model will do, it will lock a model and it will then build the map. It is mandatory, right? Once the model is logged, we cannot change the structure of our register block, meaning we cannot add the further memories and register inside this model. Okay, so if you see the literature, you will find some information related to this lock model. So once we have to define, we have to lock the model. So this, after locking the model, it will build a address map. Okay, and once the model is locked, no further structure changes can be there. Okay, should be there, such as we cannot add the further registers and memories inside a model, and it is not possible to unlock the model once the model is locked. Okay, and just end class register class, and just as a part of top class, I am defining the module. Inside this module, in module class, I'm just defining the instance of a register block, and within initial begin block, just allocating a memory for this register block, and just calling the build method of this register block. Very simple. So right now we are not considering the adapter and the sequencer and all, because we are not writing anything inside a DUT. Just for getting a flow, how we can define a register class and how we can define a register block, we have just wrote those code only. In the next video we will add all those things, adapter, sequencer, driver and all, and then we will try to understand more about this. Okay, so if you just run this code, if there is no any error, syntax error and nothing is there, you'll find it will pass, like meaning there is no any error and there is 2 warnings. You can ignore this warning as of now. So this is what simply we can define a register model, and we can define a register in our DUT. Okay, in the next video we will try to explore more about, as a part of this RAL, how we can define an adapter layer, how we can write the values inside a DUT register, how we can get the desired and mirrored value, what are different methods like set, get mirrored value, the predict method, update method, write method, read method. All the things we'll try to understand from the later videos. I will put a link of those videos which I covered as a part of RAL earlier, so that you can go through those videos, and if you are proceeding after those videos, you will find this concept easy to understand. Okay. I'll put a link of this video inside the description. You can play around with those code. So what you can do, you can define two registers in our DUT, and as a part of that you can define a register classes, two register classes. You can configure them, and you can create those classes here inside a register model, and you can play around with those code so that you will have the clear picture and clear understanding. Okay, so with this I hope you have understood a basic of register abstraction layer, and also I hope you understood that how we can define a register inside our RAL, inside our test bench architecture, how we can define a register block, how we can add the register instance, how we can configure, how we can define a map, and we can add this register inside a map. Okay. And also I hope you enjoyed this video. Okay. So thanks for watching. Thank you.